So last time we proved this convergence of kind of the simplex algorithm, not a particular simplex algorithm, but basically this process of pivoting at one point to the other and to the other. We show that there exists a sequence, a finite sequence of such pivoting operations or steps, whatever you want to call, such that you will reach the answer. You will solve the problem in finite steps, right? And we also commented that this proof actually, in the end, gives us actually also the existence of solution for a linear programming problem. It's kind of a theoretical result. So today we will look at the same problem, probably from a somewhat different angle. In the end, it will also establish existence of the optimality in a different way. So that is through convexity. Okay, so that is a concept very much being used in a lot of the high math. Okay, so to my opinion, probably this is the most interesting thing in the whole course. Okay. Then later on, there's the duality. That's also interesting. But this probably is more elegant. Okay. And the rest is just algorithm. Okay. Not to play down on them, but the convexity here is actually the core theory foundation that gives us this simplex problem. Okay. All right. So convexity. Have we heard of this name before? We say we have heard of a convex function. We have. What about a convex set? We have heard of it? Yep, nope. Never. How many of us are math majored? Okay. We never encountered convexity anywhere along the way? Right, okay. So we will go through some definition to start with. So I will define, so we're talking about sets. Okay, a set is a collection of things that share some common property, right? So we'll go through a definition of what we mean by, let's label that. So I have a set, let's call it S. Usually that's the notation. We say a set is convex if the following holds. If I have this 1 minus t, I'll explain what that is. So if this guy belongs to the set, whenever x, y are in the set, and this t here is a number between 0 and 1. Have we ever heard of such definition before somewhere? Nope? Yep. So x and y, now there are two elements in this set S, and then you can think vector, maybe, if you talk about vector space, okay? And then t is a real number. It lies between 0 and 1. So what I did here is basically some kind of a linear combination of x and y. And I formed a new element. And that one is also in the set S, okay? And if that is the case, then we call the set is convex. Okay, so what does it mean? Some geometric interpretation of this. So geometric. Let's say R2, the space, two-dimensional space. Every point in a two-dimensional space can be expressed as a vector with two elements as the x and y coordinate. Is that right? And let's say I have 2 points in my two-dimensional coordinate. I have a point P, which I call coordinate P1, P2 as the x and y, and I have a point Q, I call the coordinate Q1, Q2, okay? What will be this combination? What will be this guy? 1 minus t times p plus t times q. What would that be? If I write out its coordinate, then I will have the x coordinate. You just element-wise make this combination. So I have 1 minus t times the x coordinate of p plus t times the x coordinate of q. That will be the x coordinate of that new point, right? And the y is the same, p2, t, q2. So that will be the coordinate of that point for a given t. So as t ranges from 0 to 1, how would this behave? So you could think, I'm looking for maybe a curve in the two-dimensional space where this is your x coordinate and this is the y coordinate, and t is my parameter, and the parameter, it's a parameterized curve. Is that right? So when t equals to 0, where will I be? When t is 0, I will be at p. Is that right? That's where t is 0. And then when t is 1, where will I be? Wouldn't I be here at q by this definition, isn't it? So as t changes from 0 to 1, look at this parameterization. What is it? Isn't that a line, a straight line? Because it's all linear in t, isn't it? So this will actually give me a segment, line segment. Okay, it's a straight line. I didn't draw this so perfectly. Connecting p to q. Between them, not outside, if t is between 0 and 1. Is that clear? So this actually gives me, let's write out. Okay. As t ranges from 0 to 1, what do I get? And this actually forms the line segment between p and q, between the 2 points that I make this connecting it. Okay, and then in the special case, if p equals to q and that I have the 2 points that are the same point, then this segment shrinks down to a point, and you just stay at the point and you don't move. Is that clear? Okay, this becomes a point. Okay, the same point, p or q is the same. Is that clear? So this concept that, so now you can maybe think of this definition geometrically. If it's in the two-dimensional space, you can visualize the set, and then you can see that I pick any 2 points in my set and I draw a segment between these 2 points, then the whole segment must lie in the set. Is that right? For any t value, I will be on that line segment. Is that clear? So that's a visual way of seeing a set is convex. Okay, so let's put in another definition. So this way of linearly combining 2 elements, this particular way in this definition, it's related to a convexity, so that has a name for it. You know it's a linear combination, but in a special way. So a point 1 minus t x plus t y, okay, with specifically t is between 0 and 1. This has a name, is called it's a special combination. It's called a convex combination. Okay, of x and y. So that's what I'm defining. So this is a special way of combining, performing linear combination of x and y. And then you see that if t lies between 0 and 1, 1 minus t will never be negative. And t, of course, is not negative. It's bigger than 0, right? So you basically have 2 numbers in front of x and y. Both are positive, and they add up to be 1. Okay? So if you are thinking of x, y as two numbers, what you do by this will be taking some kind of weighted average between x and y. Okay? And the number between x and y will be the weights. Any of these language familiar to anybody? Weighted average? No? Okay. It's all right. Now let's take some examples of convex sets or not convex sets. So we'll try some examples. Okay. Let's take a very simple example. Let's say I have a set in a one-dimensional space, just the value of x. Let's say it's just a line segment, x less than between 0 and 1. So you see you have a line here, x, and then you have a point 0, and you have a point 1, and then this interval here between 0 and 1, including the end point, that's my set S. Do you think it's convex? If I take randomly any 2 points in my set, I take a point here and I take a point here, and I connect those 2 points, will this segment lie in the set? Yes, is that right? So this is convex. So any interval is a convex set, a line, okay? This also goes into 2 dimension also as well. Okay, and let's take another example. I don't know if we're okay. X, let's just do the simple one. Let me write it in a more formal setting. So, okay, let's go into a 2-dimensional space. So I can still draw it. X and y, let's say x squared plus y squared less than 1. Just be simple. What region would that represent? Anybody? If I replace this with the equal sign, that's the equation for the circle. Is that right? If I say less than equal, what does it mean? Do I take the interior of the circle or the outside? So it's a disk. Is that right? Okay, so this gives me a disk. Okay, so centered at the origin and with radius 1. Is that right? So pretend that's a beautiful disk that I draw. So the interior of that will be my set. So using the definition, the geometric interpretation, take any 2 points, connect it, the line segment must lie in. Do you think it's convex? We agree? You see, you pick any points, even on the boundary, and then you connect it, the segment is going to lie in the disk. Is that clear? Okay, so this is convex. Okay, that's just to do it like visually. Okay, you still will practice how to prove the whole thing with the definition. So, okay, so let's look at another one. Absolute value of x plus absolute value of y less than equal to 1. So what region will that represent? So you know by taking different signs of x and y, you actually have 4 equations, 4 inequalities. If x and y are both positive, then you have x plus y less than 1, right? So in the first quadrant, what will I have? If x plus y equals 1, then I get this line. Less than 1, I have the part under. Is that right? You can repeat it in the other quadrant, and you will find out that it's this diamond shape, that region. Okay. Is that convex? It is, right? So it's from visually, you see any 2 points you connect, so it's in the set. So that's also convex. Okay, the next one, okay, I will not write out equation for it. Let's say I just have a triangle or quadrilateral or hexagon or whatever. Let's say just a triangle, generic. The interior, this part. Do you think it's a convex set? Any points that in this triangle? It is, right? Okay. So these are all convex set example. All right. Let's take some other examples. Probably not so. So let's modify the set in example 2 into the following. So instead of less than equal sign, let's put equal sign. What would that set be? I'm interested in the point where x squared plus y squared equals 1. So that is an equation of a circle, isn't it? So I actually have a circle, but only the outside, not the interior of the circle, because it equals 1, right? Do you think this gives me a convex set? So in particular, this set has a hole in the interior. Is that right? So you connect 2 points in your set, and you draw a segment of line. All those points in the middle is not in your set anymore, right? So that's not convex. Is that clear? Okay. I want to put a next one, just draw a shape, a star. Should I draw a Disney star with 4 legs, or a communist star with 5 legs, or a Jewish star with 6 legs? Your vote? Disney star? Okay, don't get into politics. Disney's okay. If I can make a nice star. Okay, the interior of this star, that's my set. Just a shape. Do you think that's convex? Nope. Can you give me a counterexample? Do you know what is a counterexample? You say a statement is false. Why? You give me example to show the statement fails. That's a counterexample. Yeah. You want to try? Yeah.
If you do like the bottom point to the leftmost point, it won't go through the star.
Close to the corner, right? And then if I connect it, there'll be a part that gets out of the set. Yeah. Okay, so this is not convex. Are we okay so far? It gets complicated eventually, but okay. So, and let's say I'm curious of the next question. Let's say I know triangle is a convex set. What if I'm interested in a union of 2 convex sets? Okay, so what do you think that will be? So, union of 2 convex sets. Let's say I put 2 triangles together. Let's say I have a triangle like this, and I have another triangle like this, and I say the union of it. What will be the union of these 2 triangles? It will be Jewish star. We cannot avoid that. Okay, that's fine. So that will be the point that's either in first triangle or in the second triangle. So everything, right? It collects. So each triangle is convex. But if I want a union of 2 convex sets, do you think that is convex? No. If I just pick 2 points here, I connect, I will get out. Is that right? Okay. What about intersection then? If I know, so okay, let's pose this as a question because it's kind of important. What can I say intersection of 2 convex sets? Let's take the triangle as our example. We're not generalizing it. We're just making some observation, and later on we'll prove these. So I have 2 triangles. Where will be the intersection of these 2 triangles as I place them like that? It will be it has a name. It has to be in both triangles, right? Which means these corners are no good because only one triangle covers it, not both. Is that right? So I will have just this internal hexagon. Is that right? That will be my set. So is that one convex, at least for this example? The intersection of two convex sets? It's convex. Because you pick any 2 points, you draw a line, the segment lies in the set, right? So this is convex. Okay, later we'll show that that's a general property. Okay, so these are just visually checking by drawing line segment once you have the graph of it. So I will give another example where actually you prove it per definition, right? Because some sets, especially if it's not in 2D, if in high dimension, you cannot draw it, you will not be able to see where the segment goes. Then you have to go back to the definition and see the conditions of the definition are satisfied. Okay. So what I want to do is, let's take the diamond as our example. I want you to prove that this is a convex set. Is that okay? Prove the diamond is a convex set. Okay. And the definition of the diamond set is given here in part 3. Okay, so let's try to do this proof. So I want you to prove per definition, so you can maybe write down what I need to prove, or think about it first. So I need to randomly pick 2 points that's in the diamond, and then I need to make a convex combination of them and show that that one also lies in the diamond. Is that right? Is that clear? So let me write down what we need to prove. Okay, so let's pick randomly 2 points. Let's say x1, y1, and x2, y2. These are just random 2 points in the diamond. Bless you. Okay, so what is the definition of the set of this diamond? Well, I have some constraints. The absolute value of x plus y shall be less than 1. So I shall have the following. So for the first point, it's in the diamond. So this holds. Is that right? And the second, the point x2, also is in the diamond. So that holds. Is that right? Okay. And now I make a convex combination. Let's pick any t between 0 and 1. And I make a combination. Let's call this z. Okay, z is 1 minus t. Combination of the point x1, y1, plus t times the point x2, y2. That's a convex combination of those 2 points. So what will be the coordinate for this z here? Well, you just add up each element. So for the x element, I will have 1 minus t, x1 plus t, x2. That will be the x for this point z, right? And the y, you will be adding the y, 1 minus t, y1 plus t, y2. So that will be the coordinate of z. And what do I need to show? I need to show that this point lies in the diamond, meaning I need to show, let's write down exactly what I have to show. I need to show the absolute value of this x here plus the absolute value of this y here should be less than 1. So it's in the diamond. Is that clear? I need to show 1 minus t, let's copy it, x1, t, x2, plus the y value, 1 minus t, y1 plus t y2 shall be less than equal to 1. Is it clear? So that's what I mean by proving it per definition. Okay, just strictly stick to what the definition requires you to do. Okay, so we need to show that. We need to show the left-hand side here is less than the right-hand side. Okay? Okay, so indeed I can do so. Let's take a few steps. So left-hand side is written like this. I have a first term which has a sum in the absolute value. So a standard trick to play is to use the triangle inequality. Do we know about the triangle inequality? Let me just write here, the triangle inequality. That's a very important inequality. It basically says the sum of the two sides of a triangle is bigger than equal to the third side. That's basically what it is. And what you write down will be any number a, b in absolute value is less than absolute value of a plus absolute value of b. Is okay? That's a triangle inequality, okay? I hope we're familiar with that. So we're going to do that on this absolute value sign. So meaning I'm going to replace it with the sum of the absolute value of each and get something bigger. So I have less than equal to. And then I also know that these coefficients t and 1 minus t are both positive. So I can take them outside the absolute value sign. Is that clear? So, okay, a few steps I took there, so let's write down. So I have 1 minus t, absolute value x1, plus t, absolute value of x2. That's coming from the first one. And I do the same thing for the second. Then I have 1 minus t, y1, t, y2. Is that okay? Just triangle inequality. Okay, now I'm going to collect terms together. So the two terms with 1 minus t in the front, I will collect them and write 1 minus t outside. It's a common factor, right? So I have absolute value of x1 plus absolute value of y1. So I take this term and I formed that one here. Is that okay? And then the remaining two terms has t as a common factor, and which I would take out. So I have this. Okay. Okay? So what can you say about these two expressions in the bracket, the big bracket? What will happen to the first one? x1 absolute value plus y1. Did we assume something on that? It's on the board. That's less than 1. Is that right? Because that point is in the diamond. And x2 plus y2 in absolute value is also less than 1. Is that right? So this guy is less than 1, this guy is less than 1. And the coefficient in the front, these two are non-negative. So if I replace this by 1, I get something bigger. Is that right? So this is less than 1, and this is less than 1. So I have 1 minus t. This is less than 1 minus t, and this is less than t. Okay? Cancel out to the t. I reach the right-hand side. And I'm done. Is that clear? Okay? So you conclude that the diamond is convex. Okay. So would you like to take the challenge and show that the disk is convex? I challenge you to do that just by yourself. Try that. Per definition, see if you can reach the conclusion. All right? It might be a bit more involving, but okay. All right, okay, so let's go back to the observation that we made earlier about intersections of convex sets. And we made an observation that is, if you have two convex sets, say if they are triangle, we actually made only that observation as triangle, and then take the intersection of those two triangles, I still get a convex set. Okay. And I want to generalize on that. And this is actually, it's a very, very general property. So a proposition here, that's the third one that we have. Okay. So actually, there is a general result saying that the intersection of any number of convex sets, okay, not only two, you can give me 100 if each of them is convex, okay, and then make an intersection of it, and then this intersection is also convex. So is clear the statement? What I'm asking? You have tons of convex sets, and you make an intersection of them, and then that shall be convex as well. Okay. So let's write a proof. Okay. We want to formulate this problem. So you're saying you have many, many convex sets. So let me label them, and I call them Si. Each one has an index I, where this I just belongs to a set of index, maybe from 1 to 10, 1 to 100, some index sets. That's called capital I, okay, for the index. Okay, let this be a collection of convex sets. Okay, so each of them are convex. Okay, so what we need to show, that if I make an intersection, so are we familiar with a few notations for sets? So the union is a big U, the intersection is a upside down U, right? We've seen that. So you will write like this: the intersection of Si, I with the index. Okay, you want to show that is convex. Okay, we show it per definition. Okay, so what does it mean? Well, we'll take two elements, x and y, in this S here, and we make a convex combination of x and y and show that is also in the S. Okay? Is it clear? So that's what we were doing. So let's pick two elements, x and y. They are both elements in the set X. Just randomly I picked two. So what does it mean? That means those two elements, x and y, are in the set of intersection of all these SIs. So what is the meaning of the intersection? Any element in the intersection will belong to each of those sets. Is that right? That's what it means by intersection, right? So this means x and y should lie in every one of these SIs. That's what it means by intersection. Okay, so x and y are elements of Si for every I, basically for all the SIs. Okay, and then we also know that every one of these Si is a convex set. Okay, so hold that in your mind. Okay, and now let's pick a T. We'll do the convex combination. Let's take that and consider the combination 1 minus t x plus ty. What can we say about the convex combination? take one particular set Si, fix an I, we have an Si. I know both X and Y will lie in a Si. Is that right? And Si is a convex set. So a convex combination of X and Y will lie in the set of Si. Is that clear? For any Si. Okay, let me write it down. So for any I, what do we have? We have X, Y in Si, and Si is convex. What does that tell me? Can I call this point the convex combination X, Y? Can I call this W? Would that be okay? Consider W is the convex combination of it. So per definition of convex set of Si, then I know this W will lie in the set Si. Is that right? And this works for every I you can go through, because the I pick is generic. So what do you conclude? You find a point that lies in every set Si, so it must lie in the intersection. Is that clear? So W must lie in the intersection. And that's exactly what you needed to prove, right? So S is convex. Is that okay? It's all a bit abstract, but not too bad, I hope not. Okay, so all these discussion, in the end, I want to apply them back into linear programming. So let's try to connect back. Connect to linear programming problem that we have been working on. And then, linear programming problem can be written in many different forms. And in particular, the constraints can be written less than equal to, bigger than equal to, and blah, blah, blah. So to make the conversation a bit simpler, let's stick to standard form, okay? So I'll just talk about, if it's not in standard form, you can always add slack variable or artificial variable and make it into standard form. So the constraints will all be equal sign. Is that clear? I don't consider less than. You can discuss that, it just will be longer discussion. Okay, let's say it's all equal sign. Okay, and I want to connect this convexity into that. Let me throw at you a theorem. So we're familiar with the concept of the feasible region. Do we still remember the feasible region? That is the region where all the constraints are satisfied. Is that right? All the constraints. Okay. So I'm saying that the feasible region, let's call it S, of any of these linear programming problem is a convex set. So this sounds like a pretty grand claim, because any number of them, right? It's a convex set. Okay? So think a little bit about it, and we'll construct a proof. Okay. So think in a linear programming problem, you have this set of equations which describes the constraint. Each one has an equal sign. And in the end, the feasible region will be the region where each of them is satisfied, right? So that sentence is clicking something, isn't it? So each of the constraints gives you a set. And then all of them must satisfy. You're looking for the intersection of all these sets. And you want to show the intersection is convex. So how can proposition 3 come to my rescue and make my proof simpler? Any comments? If I want to show the intersection of a bunch of sets is convex, what will make my job enough? What does proposition 3 say? Intersection of any number of convex sets is also convex. So if I can show each constraint gives me a single convex set, then I can quote proposition 3 and I am done. Do we see that? That's all I need to show. So it becomes a very simple task in the end. Okay, let's put this down. What do I mean by that? Since now all constraints must hold. Okay, so what does it mean? This means S is the intersection of a finite set of my constraint. We know they are linear, so linear constraints. Okay, and then we use the proposition we just proved by proposition 3. If I can meet the condition for this proposition, that is, each set is a convex set, I'll have its conclusion, right? So it suffices to show that each of these, so in particular, it's just a linear constraint. A linear constraint is convex. Okay, now my task becomes very simple and very specific. If I write down a linear constraint with the equal sign and I can show that it forms a convex set, I'm done proving that theorem. Is that clear? Okay, so let's try. How can we do that? Right, so I'm concerned with only one single linear constraint. I can write it out and then just check the definition of a convex set on it. Okay, so I just need to consider now a linear constraint. So let's write it out. I could just drop the double index on coefficients. I'll just write it as some number, a1, x1, a2, x2, all the way to an, xn equals a number on the right-hand side. That's the form of the constraint in each equation in my linear programming, right? It takes something like that. I need to show that this forms a convex set, all the points that satisfies that. So let's put a star here. Okay, so per definition, what I need to do is I should randomly pick 2 points in the set and then make a convex combination and show the convex combination also lies in the set, right? That's always what we have to do. So let's try. Need some notation, so I'm going to put things on the top. So let x bar and x tilde satisfy star. So those are the 2 points in this set formed by star. So what does that mean is that I have the following. A1, x1 bar, that's how the indices of that. An, xn bar equals b, and a1, x1 tilde all the way to an, xn tilde equals b. Is that clear? I just write this out. And then I make a convex combination. I call it by something. Let's call x hat be a convex combination of these two, x bar and x tilde. So what does it mean is that, so this means I have x hat will be 1 minus t x bar plus t x tilde for some t between 0 and 1. Isn't that right? That's what it means. I'm just writing definitions. And if you look at each element in this x hat, you are just doing the same combination for each element. So if I look at x hat, the ith element of it, I'll be just adding it up. xi, xi tilde, I go through. So that's what I mean, right? By adding up two elements, you do each position, think these are vectors, and then you're just adding them up. Okay, so what do I need to show? I need to show now this x hat, need to show the following. This x hat also satisfies the same constraint. Then I'm done. Then this is a convex set. Is that right? Okay. Are we okay? Right. Okay, this, I mean, it's always the same kind of a trick, but it takes a bit space to write. But once you get a hang of it, it's not hard. Okay, so how do we prove this? Indeed, what do we have? I will plug in x star into this equation to the left-hand side, and somehow I want to show that eventually it equals b. Okay, that's what I will do. Okay, so let's look at the left-hand side. Left-hand side, I will have a1 x1 hat plus all the way to an xn hat. I want to show that eventually gives me b. So what does it give me? So I have a1 and x hat first element. If I check here, I will have 1 minus t x1 bar t x1 tilde. That will be the first one. Let me write another one. A2 will be in x hat 2. That will be 1 minus t x2. And I have that. Okay? And then you keep adding until you reach the last one. That's an xn hat, which is 1 minus t xn bar t xn tilde. So I wrote this vertically on purpose because I'm going to collect terms together. And the terms that are lined up will be the one that I will collect together. Is that clear what I will do? So each term of x bar, I bar, contains two terms, right? And then the first one with the x with the bar, I'll collect them together. They have 1 minus t in front. And then the second one with the t in the front, I'll collect them together. Is okay? So let's do that. So let's take out 1 minus t, which is a common factor. And then what do I have? Remaining will be a1 x1 bar plus all the way down to the last one, an xn bar. That's what I collected. All right? And on this column, if I collect, I take the t out. What do I have is a1 x1 tilde all the way to an xn tilde. Okay. Anybody wants to comment on those two brackets? What will be the value of each of these brackets? It's on the board. What is this guy here? all these terms add up together? Is B, that equation. Is that right? So that is B, and what about this one? Use this one, it's B. Is that right? So these two now, it's dramatically simplified. So I have 1 minus t times B plus t times B. Canceling out TB, negative and positive, all I have left is a B. And that's the right-hand side of the equation star that I want to show. Isn't that right? So I'm done. So which means the set is convex. Is it clear? And that's why we talk about convex set. It's because linear programming, the feasible region is convex. Okay? And then the property of the convex sets can be applied here for linear programming problems. Are we okay? Isn't that neat? Okay, so next theorem, well, actually only takes longer time to write. The proof is very simple. Okay, so you have this feasible region where is the region that all the constraints are satisfied. And then you are doing the optimization, minimizing or maximizing the objective function. And that function will be attained at some point in the feasible region, right? So sometimes it's attained at one point. In some examples, we saw sometimes it's attained at more than one point, multiple points. It depends on your problem. Okay, so, and those points, well, it might not be a point, that it could be a set. So we have a name. These are called the optimality region. Okay, so let me explain what that means. That is the region in the feasible region, a subset of the feasible region, where in the problem that we have seen, we're minimizing, so where the minimum value is attained. Okay, so that's called the optimality region. So I claim that this one is a convex set. If it's attained at one point, and one single point is a convex set, because you do any linear combination of that point, it's the same point, it's in the set. But if it shall not be, it shall be an actual region, then it's a convex set. It's okay? So how do you think we can prove this? Well, the proof is very much the same as the proof of Theorem 4. In Theorem 4, we show that the feasible region is convex, meaning a collection of n linear constraints in the end form a convex set. What is different between the feasible region and the optimality region? For the optimality region, you have an additional kind of a constraint. That is, the objective function takes the minimum value. Is that right? Nothing more than that. So let's put that down. And then, okay, the optimality region, what does it mean? It equals to, it's just in the feasible region, where all the constraints must satisfied, but then you put further restriction where the objective function takes the, let's say, the minimum value. Okay, so we know the objective function is a affine function, so you will have c1 x1 plus all the way to Cn xn equals negative z0 plus, it takes the minimum value, right? So let's put the negative z0 on the left, and it has to equal to the z mean, if the mean exists and you know what it is. So is that also a linear constraint? Yes, it is. So that constraint is also convex, right? And you are just adding one more convex set to the feasible region, to the intersection that you are forming. It doesn't change the convexity of the result. Was that clear? That is all, right? Okay, so this, which is you can consider as a linear constraint, and therefore convex. Okay, and then you're doing the intersection. The intersection is convex, and that's it. Okay? All right, so now we know not only the feasible region is convex, also the optimality region is convex. And actually there are more convex sets in this setting. So in the end, what do we need to do? We need to, we have this objective function, which is affine, and we take all the points in the feasible region, and we need to evaluate the objective function in this feasible region, right? And among all those values, we need to find the minimum and find where the minimum is attained. So we will be interested in the value of the objective function, or the set of the value of the objective function. And that is also convex. Okay, so we'll get into that. So let's put up the definition. I need to form that set. Okay, that's number 6. So okay, so I'm restricting myself to the feasible region, and I want to see the objective function, what values it takes. So it will take multiple values, and then I form a set. Okay, and these, and I call these values feasible values. So, and then I will form a set of all these values. Okay, so you know we have problems we ran into where that the problem is not feasible, meaning the feasible region is empty. And if it's empty, then there's no feasible values, and there's no solution. So those problems is not in the discussion. Okay, so they're all there. Right, so so the next proposition will be the set of feasible values is also convex. That will be 7. Okay, so I'll just write down the set of feasible values is convex. Okay, so before we prove it, let's think a bit about it. What does it mean if it shall be a convex? So you are taking this feasible set, which might have dimension n, because you have x1 to xn. And then you have a function, we call it a mapping, takes all these x values and add them up, and you get one single value, right? So the image of this mapping is one single real number. And for each point in the feasible region, you are returned one number. So you're talking about a convex set in a one-space dimension as the feasible value set. Is that right? If you say that set is convex, what does it mean? You have just one value, Z, a real number in R. And then you say it has to lie in a convex set. So let's think. If I just have a number, we already saw in one example that is an interval is a convex set, right? And if I shall not have an interval, if I shall have an interval like this and another interval like this, do you think that can be a convex set? If I take a point here, take a point here, I draw a line in between, I get out of my set. That is not convex. Is that right? So if a one-dimensional set shall be a convex set, it has to be one single interval. Is that clear? So that is what I want you to catch your attention. So let's put a remark before we prove it. So remark, this means this set is an interval. Okay? It might be a bounded interval if your objective function is bounded above and below, or for some reason, or it could contain a half ray that is might be not bounded above or might be not bounded below, but it will not contain a union of several intervals that's not that's distinct, that's not connected. All right? Is it clear? Okay. Okay, let's try to prove this proposition. Okay. We have to prove that this set here is convex. Again, the proof has to be done per definition, meaning I need to take two values in this set and then make a convex combination of it and say that combination is also in the same set. Is that clear? That's always the way to go. No other way. You have to stick to the definition. Okay, so let's write down the objective function because we know what it looks like. Let's say the objective function is the following. Z0 is a number, C1x, Cnx be the objective function. Okay, let me write it here. Okay, so that's the objective function. And let's say I randomly pick two values that's in the set of feasible values. Let's call it Z bar and Z tilde be two feasible values. Okay, so what does it mean? That means they are values of the function z taken at some feasible point in the feasible region. Is that right? So I could associate each of this with one point in the feasible region where z attained this value. Okay? Let's say attained at two feasible solutions. Let's call it x bar, x tilde. They are feasible, okay? Respectively, one for each. Okay, so what does that mean? I'm going to write out what I mean by that. So this means z bar equals the objective function evaluated at x bar. So C1 x1 bar, Cn xn bar. Okay, Z1 is attained there, or Z bar is attained there, and Z tilde is attained at x tilde Okay, now I do a convex combination of these two. Let's call the combination z hat, 1 minus t z bar t z hat. Okay, that's a convex combination of the z bar and z tilde. I need to show that z hat is in the set of the feasible value, meaning I need to show that there exists a point in the feasible region such that z hat exactly takes this value. Is that right? Need to show that there is a, let's call it x hat, in the feasible region, feasible, such that z hat equals to the feasible solution. Okay, let me write it out. So I need to show that z hat equals to negative z0 plus c1 x1 hat cn xn hat. I need to show that there exists one. Okay, so indeed that can be achieved by, we actually know because everything is linear. So what will be a good candidate for this x hat that I want to find? How about I do the same linear combination for those two x points? If I just do that, it will work. So let x hat be the same linear combination of the feasible solution. And then I claim that will work. Okay, and let's check. So I need to show this, right? Then, okay, so I need to show the, okay, let me copy. So negative z0 plus c1 x1 hat plus all the way to cn xn hat. I want to show that this actually equals z hat. Okay, so let's argue a little bit. How can I do that? So that will equal to what? Okay, so one trick I do, I will split z0 into the following. I can write it as 1 minus t z0 plus minus here t z0. So negative z0 equals that. You can easily verify that's true. Okay? You add up the coefficient, it's 1. You just get negative z0. Okay? And then c1 times, okay, what is x1 hat? Well, it's a combination of these two. So I will have 1 minus t x1 bar t x1 tilde. That will be the x1 hat, right? That's the combination I make. Okay, plus dot, 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 plus until the last one will be cn x hat. Well, it will be this expression where I put n here. So 1 minus t xn bar t xn tilde. That's what it will be. Okay, so it's always the same trick that I keep playing. Now I'm going to collect terms together and in a smart way choose some good regrouping. I will take all the terms with 1 minus t together. That's a common factor of all those terms. Okay? So if I take that out, I will have 1 minus t. I take that out. I get negative z0. And then I have this plus c1 x1 bar. And then I have many, many terms I will collect until the last term I'll get cn xn bar. That's like, I take half of all the terms out. All those with 1 minus t in it. Okay? And then The rest will be grouped together, and I will take t out, because t will be present in all the other terms, these ones. Okay, and then I have negative z0 from the first, and the second I will have c1 x1 tilde, and there are many, 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 until I reach the last one, cn xn tilde. It's basically the same thing I'm doing. All these three proofs is all just rearrange them. These terms could be reshuffled with no problem because it's all linear. Okay, so now tell me these two brackets, what are they? It's somewhere on the board, you know, you have to find it. So what will be the value for this first bracket? It's on the board. Isn't that z bar? This is z bar. What about the second bracket? Z tilde? It's that one, is that right? Z tilde. Okay, and so I have 1 minus t z bar plus t z tilde. Isn't that exactly the definition of z hat? It's the combination of those two z values. This simply equals to z hat. And that's what I wanted to prove. Is that right? Then I did it. So done. So that set is convex as well. Oh, it's 12:30. I didn't cover as much as I did in the other class, but okay. We'll do the rest next class then. It's time up, right? It's 12:30, yeah. Okay.